Welcome back, everybody, to a new tutorial from NeuralNet.ai. I am your host, Phil Tabor. If you're new to the channel, I'm a physicist, former semiconductor process engineer turned machine learning practitioner. If you haven't subscribed yet, go ahead and hit the subscribe button so you don't miss any future reinforcement learning tutorials. When we left off in our previous video, we just finished up the bulk of our OpenAI Gym compliant reinforcement learning environment. Today we're going to go ahead and code up a Q-learning agent and the main loop of the program to see how it all performs. So let's go ahead and get started. So the first thing we are going to need is the magic squares, right? If you recall, the magic squares are the teleporters in the grid world that either advance the agent forward or backward. So the first one is going to be at position 18 and dump out at position 54, so it'll move it forward. And the next one will be at, let's say, 63 and dump out at position 14. So teleporter A will advance the agent through the grid world, and teleporter B will send it back to an earlier square. So we need to create our grid world. We use a 9x9 grid and pass in the magic squares we just created. Next up, we have to worry about the model hyperparameters. So if you are not familiar with that, let me give you a quick rundown. These are the parameters that control how fast the agent learns and how much it chooses to value the potential future rewards. So the first parameter is alpha. That is our learning rate. 0.1. A gamma of 1.0 tells us that the agent is going to be totally farsighted. It will count all future rewards equally. An epsilon of 1.0, this is of course the epsilon for epsilon greedy action selection. So it will start out behaving pretty much randomly and eventually converge on a purely greedy strategy. So Q-learning is a tabular method where you have a table of state and action pairs, and you want to find the value of those state action pairs. So to construct that, we have to iterate over the set of states and actions. State space plus and env.possible actions. And you have to pick something for an initial value. It's really arbitrary, but the cool thing about picking 0 is that we're using something called optimistic initial values. What this means is that since the agent receives a reward of -1 for every step, it can never have a reward of 0, right? Because there's some distance between the agent and the exit. So by setting the initial estimate at 0, you actually encourage exploration of unexplored states, because if the agent takes a move, it realizes, oh, I get a reward of -1, that's significantly worse than 0. Let me try this other unexplored option. So over time, it will gradually explore all the available actions for any given state, because it's been disappointed by all the stuff it has previously tried. Just a fun little fact. We want to play 50,000 games. We need a way of keeping track of our rewards. NumPy array will do just fine, yes? So now let's iterate over the total number of games. And I like to print out a marker to the terminal so that way I know it's actually working. So if every 5,000 games, just print that we're starting the ith game. At the top of every episode, you want to reset your done flag. You want to reset your episode rewards so you don't accumulate rewards from episode to episode. And of course, you want to reset your environment. Oh, let me scroll down here. There we go. You want to reset your environment just as you would with any OpenAI Gym type problem. Next up, we begin each episode. So while not done, we want to take a random number for our epsilon greedy action selection. So we're going to just make use of this max action before we define it. Q, observation, and env.possible actions. And what that will do is, we're going to write it here momentarily, but what it's going to do is it is going to find the maximum action for a given state. So if the random number is less than 1 minus epsilon, we want to do that. Can you guys see that? Yep. Otherwise, we want to take a random sample of the action space. So we have to write these two functions. Let's do that quite quickly. So the action space sample is pretty straightforward. We can just return a random choice from the list of possible actions. And that's the reason we chose a list as that data structure, just to make it easy. Next up, we have the max action function, but that doesn't need to belong to the class. That takes the queue, the state, and the set of possible actions. We want to take a NumPy array of the the agent's estimate of the present value of the expected future rewards for the state it's in and all possible actions. A in actions, and then we want to find the maximum of that. And that's just an index, so we want that's just an index, so we want to return the action that actually corresponds to. All right, that's all well and good. Do we need more space? Let's do a little bit more. There we go. So next, we want to actually take the action. So we get our new state, observation underscore, reward, done, and info. env.step action. And next up, we have to calculate the maximal action for this new state so that we can insert that into our update equation for the queue function. So let's do that. And we're not worried about epsilon greedy here because we're not actually taking that action. Next up, we have to update our queue function for the current action and state. And that's where our alpha comes in. Word plus, make sure that is visible to you. Reward plus some quantity, which is gamma, our discount factor, times q, observation underscore, action underscore, so the new state and action, minus q observation action. Let me tab this over. There we go. Nice and compliant with the PEP style guides, right? Mostly. Okay, so this is the update equation for the queue function. That will update the agent's estimate of the value of the current state and action pair. Next up, we just need to let the agent know that the environment has changed states, so you set observation to observation underscore. And that is it for queue learning in a nutshell, folks. That's really that straightforward. So at the end of each episode, we want to decrease epsilon. So that way the agent eventually settles on a purely greedy strategy. You can do this a number of ways. You can do it, with a square root function, a log function. I'm just going to do it linearly. It's not that critical for something like this. So it's going to decrease it by 2 divided by num games every game, so about halfway through it'll be purely greedy. And at the end of every episode, you want to make sure you're keeping track of the total rewards, which is something I forgot up here. Yeah, so one thing I did forget is to keep track of the total reward for the episode. Don't forget that, very important. And at the end of all the episodes, you want to plot the total rewards. And that is it for the coding portion. Oh, one other thing, I take it back. So let's scroll up here. I do want to show you the environment, so let's just do that, env.render. And the purpose of doing that is so that you can see how many moves it takes the agent to escape from the grid world. That will tell us if it's doing good or not, right? Because there's a minimum number of moves it takes to escape. So I'm going to fire up the terminal and go ahead and get that started. 1 second. And here we are in the terminal. Let's go ahead and run that. And you can see here that we start at the top left. So it takes 1, 2, moving to A out is free. So 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, 11. And the 12th move is free because it's the exit to the maze. Sorry, to the grid world. So total reward of -11 is the best the agent can possibly do. It's gone ahead and plotted, so let's check that out. And here is the plot. And you can see that indeed the agent starts out rather poorly, exploring, finding suboptimal routes through the grid world. But eventually, and about halfway through here at 2,500 or so, 25,000, you can see that it settles on at least a constant value. Let's prove that it is the maximal value of -11. And you can see that it's 10.97. That is close enough for government work. So you see that the agent is able to actually solve the maze, the grid world, I keep calling it a maze, is able to solve the grid world using the Q-learning algorithm. Now this isn't surprising, we would expect this. What's novel here is that we have created our own reinforcement learning environment that uses a very similar format to the OpenAI Gym. So anytime you want to create a new environment, you can fire this video up and use the set of code here just as a template for your own projects. I'm going to put this up on my GitHub. I'll link that down below, and I'm also going to write up a tutorial in text form and upload it to neuralnet.ai. I don't know if I'll have that done tonight. I'll update the description with it. And that's if you are if you consume text more easily than video, then you can go ahead and check that out. I hope this has been helpful. Make sure to leave a comment, subscribe if you haven't already, and I hope to see you all in the next video.